I just defined what it is POS and algebra. So it is a graded commutative algebra with a Lie bracket of degree n-1 compatible with the product. So here is the properties that it's compatible with the product, right? So now let me just say, so what I mean by the bracket of degree -1, it simply means that when you take the degree of AB, so the degree of this element, assuming that both A and B are pure, so then we are going to get degree of A plus degree of B plus n-1, right? So we want the bracket to be of degree n-1. But we still put POS of n instead of POS n-1. I think that like initially when I was using this notation, I was denoted by POS n-1, but lots of people were using POS of n, so that's why I switched to this notation POS n. So POS n is just the homology of n-dimensional cubes. So let's see geometrically what exactly this means, right? So first of all, let's look at the n-dimensional disk. So let's consider dn of 0. So dn of 0 is configuration of 0 disks, but we still want to view it as a point. And you know, when we compose with this guy, we simply forget the disk, right? So we can forget a disk in configuration just by inserting this empty configuration, right? So and so dn of 1 is also, it's actually a constructible space. It's a configuration space of just one disk, right? And this space is constructible, so it's homotopy equivalent to a point. So it's not a point, it's homotopy equivalent to a point. It's constructible. And dn of 2 is homotopy equivalent to configurations of 2 points in Euclidean space, right, or 2 disk and a unit disk. And there exists natural projection of the space to Sn-1. So what we do, we just look at the direction of the, so when you look at the centers of the disk 1 and 2, you look at the direction of between 1 and 2, right? So you might have seen the map. So there is natural map from configuration of 2 points in Rn to Sn-1, which is homotopy equivalence, right? And what you do, you just, as I said, you just look at the direction of, you know, x2 minus, which can be expressed as a formula by taking just x2 minus x1 divided by the length of this vector, right? So this map, it's a homotopy equivalence. So why? Because it's a fiber bundle with contractible preimage. And so which means that, so now if we look at the homology, right? So just before that, we saw that the homology of dn in degree 0, it is just the same as POS of 0, right? POS, well, we have bracket of degree n-1 here. Plus n of 0, so it is just actually let me use integers. So we deal with the homology, so I'll be just using integers. Z, so it's operator in the category of commutative rings, graded commutative rings. dn of 1 is also, it is just n of 1, it is just z. Right, it is spanned by here by the unit and here by the x1, right? But degree 2 homology, right? So we know it is a homology of a n-1 dimensional sphere, and now it is spanned by one element, the product, and we have also the bracket. And this is generator of degree 0 homology, and this is generator of degree n-1 homology, right? So that's how, like, geometrically what they corresponds to. So essentially x1, x2 is just configuration, just any configuration of 2 disks. You just take any point, for example, this one, right? So you see that this product is not like, it's not commutative, it's not associative, but it is homotopy commutative and homotopy associative. So that's why on homology it defines a commutative operation. And so this is a representative of x1, x2, just any point there. And for the bracket, what we want to do, we want to take the one disk, turn around the other one. So what we can do, we can make second one turn around the first one, making a sphere. So, and this exactly is the generator of the of this class. So which is -1 to the n x2, x1. So sometimes it is symmetric, sometimes it's antisymmetric. And that's essentially because the central symmetry of the n-1 dimensional sphere change the sign. So it's like if you have if n is odd, then orientation is changed, and when n is even, orientation is not changed, right? So exactly we have this property. And how we can see that x1, x2, x3 is equal to x1, x2 times x3 plus x2, x1, x3. So how we can see this compatibility property? So we see that this picture means that point 1 goes around disk 2 and disk 3, right? So we have that disk 1 goes around disk 2 and disk 3, but what you can do, you can split this picture in two, right? So you can just kind of draw a plane, and then you can make disk 1, follow this sphere or follow this sphere, right? And we obtain two cycles, and the sum of these two cycles is exactly, this one, right? So therefore, we get this compatibility property. Like it's a little bit less trivial to show that we have also Jacobi relation, but it is true. So we do have Jacobi relation. So when we have x1, x2, x3, right? So plus x2, x3, x1 plus x3, x1, x2. So it's equal to 0. I should be a little bit careful with the signs when n is even. I should be a little bit careful. So I'm not 100% sure that the signs are right. Okay, so that's about the homology. And so you see that like elements like this can be seen as like if you want to describe this element. So this element can be described as a product of two spheres, right? So like Sn-1 times Sn-1 gets mapped to configuration of 3 points in Rn, or configurations of disks Dn of 3, right? And so what's happening, we have first point 2 goes around point 1, and also point 3 goes around all of them, right? And so that will be a way to represent represent the classes, homology classes, by explicit cycles. And these cycles, for every Poisson monomial, we are actually going to get exactly a product of spheres. So as another example, when we can take x1, x2 times x3, x4, so this element lives in Poisson n of 4, right? And so what we do, we just take disk 2 goes around disk 1, and disk 4 goes around disk 3. Right. So, and it's also going to be represented by the product of two spheres. Right, so it's all part. It's all sitting inside the unit disk. So that's a nice geometrical representation of the operad of little disks, of the homology of the operad of little disks. So, okay, good. So now let me go here. Well, since we started to speak about the homology, so let me also mention what is the homology of the little disk operad. So cohomology of the little disk operad. So let me just describe the cohomology of configuration spaces. So first of all, you see that we have projections, right? So we have projections CK Rn. We can project to configurations of 2 points in Rn, right? So just we forget all but i's and j's points, right? Configurations of x1, xk goes to just configurations of like we just get point xi. It's going slowly. Xi and xj. Right, and this is a homotopy equivalent to a sphere, right? So this is a sphere. So what we can do, we can take the generator omega of degree n minus 1 cohomology, right? And take its pullback. And so we defined alpha ij as the pullback of this class. And it turns out that the cohomology algebra, so theorem, Arnold and Cohen, so it was same paper for Cohen, 70s. So it describes the cohomology algebra cohomology of configuration space of k points in Rn is torsion free so generated by all these classes alpha ij and relations are the quadratic ones. So first of all, we have that alpha ij is minus 1 to the n alpha ji, right? And this is because like if we have central symmetry of the sphere Sn minus 1, right? When we take central symmetry of the sphere, then orientation changes depending on the parity of n, right? If it's even or odd, right? So the orientation can change, and that's why we have alpha j is related to alpha gi, by this formula. So also we'll have that the square of alpha j is 0, and this again follows from the fact that the square of the top homology class is 0, right? So this is true for the cohomology of the sphere. It doesn't have cohomology in degree 2n minus 2. So, and pullback preserves the relations. And most important relation is the so-called Arnold relation. So we have alpha ij, alpha jk, plus alpha jk, alpha ki, plus alpha ki, alpha ij is equal to 0. So this is the description of the cohomology algebra. And first of all, what we can do, so there exists a little bit more kind of geometrical way to see the classes, not geometrical, more kind of combinatorial way to see these classes. So what we can do, we can assign to any monomial in this algebra, we can assign a graph. So assign, so let us assign a graph to each monomial. So just as example, if we have a monomial alpha 1, 2 squared, alpha 2, 3, alpha 3, 4, right? So what we can do, we can look at the points 1, 2, and 3, 1, 2, 3, and 4, right? And so we get, we need to take two edges, alpha 1, alpha 2, and actually we can also orient them, right? Because we know that alpha ij is not exactly alpha gi, but equal only up to a sign. So then we have alpha 2, 3, and then we have alpha 3, 4. Right? You see that we can always assign a graph, and little lemma says that so lemma says that a monomial is 0 is 0 if and only if the corresponding graph is not a forest. Graph is not a forest. Yep. So, like for example, this guy is actually 0 in the algebra, and it is 0 because alpha 1, 2 squared is equal to 0. Less trivially, if, for example, we had a graph like this, like if it has some cycle like this, then one can show that it follows from the Arnold relations, and you know, the fact that alpha j squared is 0, right? From, you know, like a relation like this, it is 0. It follows that actually any such monomial is 0. So this both guys are actually equal to 0. And the monomials that we that are non-zero are always forests, right? So it's going to look like this. So we have 1, 2, then we have 3, 4, 5, 6. Right? This would be an example of a monomial which is not 0.
So you mean by forest a union of trees?
Right. Forest, it means disjoint union of trees. Right. So there is no cycles. In example of a forest would be element like this. So no edges at all. Right. And this is just the unit in the corresponding algebra. Right. It's also a monomial, but it's just a unit in the algebra. Okay. So. corresponds to just 1. So next, let's understand the duality between homology and cohomology. How these classes pair, in between. So duality between homology and cohomology. Between homology and cohomology. And actually, well, first of all, it's quite easy to see that if we have, when we look at the homology or cohomology of this configuration space, right? So the homology is going to be concentrated in degrees 0, n minus 1, twice n minus 1, and up to k minus 1 times n minus 1. Right. So this is the case when we have the Lie part of the operad. Right. So this is the same as the plus n of k. Right. So when we have only Lie operations, right? So like, or in terms of trees, we see that the dual is going to be just the corresponding forests, right? So the corresponding graph is going to be a tree. Like for the maximal degree, it's really duality between the Lie operad and the space of unit trivalent. So space between Lie operad and the space of trees modulo the Arnold relations, modulo the three-term relations. So how we can see the duality? So the idea is as follows. So if we have, like, it can be defined iteratively. So when we have just xi, we just send it to the graph I. So, but when we have a bracket between A and B in our operad, so what we are going to do, we are going to take the sum of all possible ways to connect A with B. So we take the sum over all possible ways to join A with B. So we need to draw an edge which goes exactly this way. Right, and we take the sum over all possible like A is in A and B is in B. By this I mean in one of the vertices. Let me just give you an example. So when we have x1, x2, right? So it's going to be sent to this graph, right? So, but when we have say x2, x3 bracket with x1, so we define it iteratively. So first we, for 2 and 3, we know that we are going to get 2 and 3, and then what we do, we need to connect 2 and 3 with 1, right? And there are two ways to do it. So we put this edge Somehow my program became very slow because I never used very big files, like 2 hour stocks I never give. So I should probably like start from blank, next time, like after break. So we have this graph, right? And actually it's important to know in which order the edges appear, 1 and 2, and also the second graph is going to be 2, 3, and 1, and then we get edge like this, right? And this is like 1 and 2. And so what this formula tells us, it tells that this class is going to pair non-trivially with this monomial alpha 2, 3. alpha to 3 times alpha to 1, and it's going to pair non-trivially with this class, alpha to 3, alpha 3 1. Right, so it says that like if you take any other tree different from this two, the pairing is going to be 0. But with this two, the pairing is going to be exactly 1. Right, so it means that like this homology class evaluated, so this evaluated on this one is exactly 1. And since other trees don't appear, so this evaluated on, if you take a different tree, like if you take, say, alpha 1, 2 times alpha 1, 3. So it is going to be 0. So the pairing between this and this homology class are going to be 0, right? Essentially because it doesn't appear in our sum. And so the corresponding tree is going to look like this: 1, 2, 3, and you know, it doesn't appear here, therefore the pairing is going to be 0. Okay, so is it clear, guys? Is it clear?
Where the product is mapped, like x1 times x2.
We have a product in cohomology, right? So cohomology algebra we just described. So cohomology algebra is generated by this alpha ij.
No, sorry, on the left, when we do the product on the left,
but
on the Poisson.
But left part is homology. So homology of a space don't have a product.
Isn't the part of the Poisson algebra? No.
Well, this structure is a structure of an operad, right? And you know, if you just take the configuration of k points in Rn, it's not an operad. It becomes operad when you consider them together, like if you consider like all sequences of spaces. And so it comes from like the way you insert one configuration inside you know, the other, right? So like in the little disk operad, what you do, you take configuration of disk and insert inside one of the disks, right? So, but if you consider just a configuration of like you fix the number of points in your configurations, you don't get any operations. You just have a vector space structure, just like the model, graded model structure. And, but you can describe it as a certain subspace of the free Poisson algebra, right? But you cannot multiply those guys. You can kind of compose when you use other configuration spaces, right?
Okay, so in Poisson K, you don't have the symbol ABC, for example.
No, you don't have. It's always like if you want to represent it explicitly. So if we have, you see, we have this Pois of n. I don't know, somehow it disappeared. Maybe it was. Okay, let me check. Okay, so. Just a second. So I need to share. Okay, but somehow it doesn't see that. I need to switch them out. Okay. Okay, so now you must be able to see what I'm sharing. All right, so so we see we have description of the homology, but right, so this is our description of the homology in terms of Poisson, right? And so by A and B, I really mean some brackets. So it's actually going to be some kind of brackets, right? So I want to define the pairing. So how we pair homology with cohomology classes.
Mm-hmm.
And like typical element in the homology is going to look like this, like x1, x4 times x2, x3, like let's say x1, x2, x2, x3, x5.
Yeah,
right?
exactly. Yeah.
Right. And you see that first of all we get a partition, right? So we had that 1 and 4 partition together, and 2, 3, and 5 partition together.
Mm-hmm.
Right. And essentially, and the same happens for the forests. If you have a forest, so we also get, your graph partition your set of points into, connected components, right? So, and what we need to have forest which is also partitioned the same way, 2, 3, and 5.
Okay, so like product is mapped to disjoint union, say.
Right. So first of all, we have this partition to disjoint union, and then we need to explain what happens with every connected component, how it pairs.
Mm-hmm.
Right. And to see what happens with the connected components, we have this iterated recursive procedure. So first of all, when we have a CXI, we just send it to the vertex I. Right. But when you have A, and by A I really mean some bracket, some iterated bracket, and B is also iterated bracket.
Mm-hmm.
And what you do, you start with A and B, and you draw an edge by choosing arbitrary point in A and arbitrary point in B.
Mm-hmm.
You see, like for example, when we have x1, x2, there is only one way we can do. We can just draw this edge, right? But when we do here, we get two possibilities, right?
Mm-hmm.
And more generally, it will be cardinality of points in A times cardinality of points in B. And what's important is that if you have some forest which doesn't appear, in the sum, it means that the pairing is zero, like with this corresponding forest. Like for example, the pairing with this element is going to be zero because it doesn't appear in the sum. And the pairing with, and actually every forest always appears either with coefficient 1, -1, or 0, right? So which means that the pairing is always going to be like either 0, 1, or -1. With like every Poisson monomial is going to pair with every forest modulo this Arnold relation, three-term relation, always like 0, 1, and -1, and to determine what exactly it is. Well, first of all, we see how they partition into sets, right? And like what partition we get, connected components of this set, and then we do this recursive operation. Okay.
Okay. Thank you.
Right, and really, the idea is kind of quite simple. Like, for example, why, maybe I should explain geometrically why, this class, when evaluated, it's a homology class, right? So why, well, evaluated on this guy, it integrates you to ±1. So let me just explain you. So it's actually very natural, right? So so what we have x2, x3, x1, right? And we have, so what was this guy? I've already forgot. Alpha to 3, alpha to 1. Alpha to 3 times alpha to 1, right? But you remember that, so what is our configuration is point 3 goes around point 2, right? And point 1 goes around both of them, right? But you can assume that this part is very small. This part is, you can think about it as something very small, right? So it's really tiny, right? And therefore, when you take alpha to 3, this guy, no, I don't want alpha to say, I take alpha to 1. So let's take alpha to 1. Then alpha to 1, it's going to be, vector which goes, in between the two, right? Goes like this. And it's integrate to, it's a spherical class, so it's going to integrate, right? So when you take pullback, so remember that this class is really represented by the product of two spheres, right? And the thing is that we have, so this guy goes to configuration of 3 points in Rn. So actually my software is very slow, probably too much information. It's not. No, I have some technical issue. No, I need to. No, it's not. So I don't know. Somehow my software is not working now. I'm sorry about that. So I probably can't write anymore. Like I can't write anymore. So
can you start a new document, like erase?
Yeah, I need to save this one, and I don't want to erase, but let me save it.
Yeah, it's better.
Yeah, but unfortunately, it's not saving. It's not saving. Probably I need to start some other. I think that. Okay, so let me stop sharing this one and start sharing something else. Okay, so let me try share this one. Okay, so. Okay, so now probably it's going to work better because I cleared the canvas. Okay, so now let me write it down. Okay. Okay, so we have again. So we have x2, x3. No, I think that this software is just no, it's not working. So I need to maybe. Oh no, it's working. It's working. So we have like x2. Yeah, no, it's actually it's stopped. It's not. Maybe I have problem with the pen. Maybe the pen doesn't have battery anymore. I need to, when I next time go for the break, I need to put it on charge. Check if it's working now. Okay, so like when we have x2, x3, x1, right, and we had before the monomial alpha to 3, say alpha to 1, right? So you see that this class can be represented by the product of spheres, Sn minus 1 times Sn minus 1 to configuration space of 3 points in Rn, right? And let's have that point 3 goes around point 2 and point 1 goes around both of them. And you see that alpha to 3 is also obtained as a pullback of the map to configuration space of 2 points in Rn, like not just spheres. Actually, it's just spheres. You can take projection to spheres, Sn minus 1, Sn minus 1. And so these are our projections pi to 3 times pi to 1. And the point is, when you take this composition, it's just it's a degree 1 map, and so when you integrate it on this Sn minus 1 times Sn minus 1, you are going to get well, plus minus 1 depending on the sign conventions. So, well, in this case, it's going to be 1. So, is it clear? Okay, good. So, and in general, every time we are going to get like map from the product of spheres to another product of spheres, right? And we just pull back these forms and just need to be careful whether degree is 0 or degree can be plus either 0 or plus minus 1. Right. Okay, good. So maybe I just say like very nice property of this little disk operad is that it is formal. Or maybe instead of saying this, maybe I just say what are algebras over little disk operads. These are also very important. This is also very important statement. So okay, so algebras over little disk operad over Dn. And there is very important examples, as I said, is a loop space. So these are so-called iterated loop space on a pointed space X, right? So this is a space of maps, continuous maps from the pair Dn and its boundary Sn minus 1 to the pair X and the base point of X. Right. So for this space, we can naturally define the following maps. So we have a Dn of k. So we have maps Dn of k times omega n of x taken k times goes to omega n of x. Right. And so how it works? So given configuration of disks and given, say, f and g, like f1 and f2, right? So since here we have 2 disks, right? So what we are going to do, we are going to rescale f1 and f2, and on the first disk we are going to use f1, on the second disk we are going to use f2, and in the complement the complement is going to be sent to the base point of x. Okay, so that's how this action map is organized, and by adjunction this gives us a continuous map from Dn of x to continuous maps from omega n of x to the k to omega n of x. And this is exactly the case component of the endomorphism operad of the space omega n of x. So, which means that, sorry guys, I made a mistake here, it's just Dn. It's just Dn. So we have a map from, sorry, Dn of k. Right, so we get a map from, and this is the case component of the endomorphism operad, and so as a result we get a morphism of operad from Dn of k, sorry, from Dn. From Dn we get morphism of operad to endomorphism operad of the space omega nx. And therefore omega n of x is, so this is morphism of operad. Right, and therefore omega n of x is a naturally Dn algebra. And there is an important theorem of May and Boardman-Vogt. So theorem which says that if X is a Dn algebra and pi 0 of X is a group. So notice that pi 0 of X, just kind of, let me say it in the comments, that pi 0 of X is pi 0 of Dn, which is just the commutative operad algebra. So in other terms, pi 0 of X must be a commutative monoid. Well, actually, it's commutative if n is at least 2. It's commutative or associative. Commutative or associative. You can get associative operad if n is 1. Right. So, but on the level of pi 0, it's either commutative operad or it's associative operad. Therefore, pi 0 of X must be either an associative monoid or associative and commutative monoid. And so in case it happens to be a group, so in this situation, so when it's a group, actually we get that every connected component has the same homotopy type. And moreover, it's actually equivalent to an iterated loop space as a Dn algebra. Then X is equivalent to omega n y for some y, for some point in space y, as a Dn algebra. So, and this means that X, actually there exists some zigzag of Dn algebras with some guy in the middle, so and then we have omega n y. So this is equivalence, but also homomorphism of Dn algebras. So morphisms of Dn algebras. So not only it's equivalent as a space, but also it's equivalent as a Dn algebra. Okay, probably that's it for today. So next time I'm going to speak next Thursday, right? No, not next Thursday, Thursday after.
No, in 2 weeks.
Right, in 2 weeks. In 2 weeks. Okay, good. So I realize that I should be careful with myself